Okay, so this week let's look at the 5 easier problems of the East Central North America problem sets from 2016, and we'll go through these one by one, and some will be easy and some will be harder, but these are the 5 problems that were solved the most often in the actual contest. So let's get right into it. The first problem, it's called foosball dynasty. It's not necessary uh, range and level of difficulty. So anyway, so basically, if you read the problem, there's a game where each team, the 2 teams, have 2 players. One plays offense and one plays defense. The 2 teams are black and white, and at any one time, 4 people play. There's black offense, black defense, white offense, white defense, and so on. And then there might be a bunch of other players that are waiting in line to play. And on each point, the scoring team switch positions. So if the white scores the point, then the white offense becomes a white defense and vice versa. And then the team that lost the points, the offensive player becomes a defensive player, and the defense player moves back to the line. So there is a line of people that are not playing, and then they're waiting for the turn, and the person at the front of the line becomes the new offensive player of the team that lost the point. So based on these rules, a team that continues scoring consecutive points gets to play together until the other team breaks the streak. Each such streak of points creates a dynasty for the winning team. Dynasties can be short-lived or long-lived, but they're always broken in when the opposing team scores a point. The winners of this variation of foosball are the players that can create the longest dynasty. Okay. Input contains starts with a line containing an integer and represent number of players. It's only up to 10. The next line contains n names of all participating players. The first 4 are the names of the first four players who initially arrived. The first one is white offense. Second, it's black offense, white defense, black defense. And then the remainder get in line to wait for the turn. Final line contains an unempty string indicating which side score each point. W means white, B means black. Maximum length is 1,000. Okay, so everything is pretty small, and you just have to basically do some bookkeeping. So display the team that has achieved the longest dynasty. If more than one team ties for the record, then display each of these teams in chronological order when a record was set, 1 team per line. When displaying team names should be displayed in the order in which the players arrive at the table for that team. Know that it is possible for the same team to appear more than once in the output, potentially with player names in different order. So this is basically just a big bookkeeping exercise, right? So here, right, so if you look at this string, just by looking at this string, you know where the dynasties are, because you have substrings of length 2 that are the same, right? And this is length 1, length 1, length 2, and so on. So you know that the longest dynasties is 2, and the players that are playing in the white team or black team at the time are the people that you want to print. And here there's only 1 winning streak, so there's only 1. So if you want, you can start out by reading this string and look for the longest consecutive letters, and that will tell you what is the length of the streak you're looking for in the dynasty. So I would probably do that first, to scan this list and figure out what is the length of the dynasty. And then I process it a second time and keep doing bookkeeping of who is playing and where, and what the line is. And then whenever I hit that number of winning streak, I would print out the name of the people. So I'm not going to write the code, but I want to kind of say a little bit about what we need to keep track of. So there's going to be a line of people, and that's going to be a queue. You probably just want a queue of string, right? At the beginning, you put in everybody that's not the first 4 people just into this queue, and then every time when somebody kicks out of the game, you put it in the back of the queue. When you need to pull somebody into the game, you pick it in the front of the queue. So that should be fairly straightforward. Now, in terms of the 4 people, so you would have black and white. So my suggestion, perhaps, is to basically just take, let's say, call it team, and we will convert it basically into 2 indices. The first index would be, are you black or white? And then the second index would be, are you offense or defense? Now you can decide how you encode this. You can decide to make it 0 and 1. Or you can say, well, forget about 0 and 1. You are told that you have black and white, so why don't I just use 256 and then index it with the character B and character W. Now, for the offense and defense, it doesn't make sense to index it with something other than a code, because there is no, in the problem, there is no other way to define an offense and defense. But in the problem, there's a string that tells you black and white using the characters. And if you use the character as an index, you might be able to just look up the character and use that instead of converting B and W to 0 and 1. So that's probably what I would do. And of course, initially you just set the 4 initial players there. Now, there's something else that maybe you haven't thought about yet. When you print out the people, you're supposed to print out the names of the 2 people in a team, but you're supposed to print out the names so that the first one is the first one that arrives, and the second one is the second that arrives. So it's not just offense or defense, you have to know which one arrives first. So you're probably going to have to also store the time at which these two people came to play. Like this, or if you want, you can combine these into one single array and use a pair in string, perhaps. Either way, it doesn't really matter. And then the whole thing is just a matter of simulating, right? So you have a queue of people, and then you have your 4 positions. And then every time somebody scores a point, the team that scores, if this is a winning point, then you have to swap these 2. So this is offense and defense. Then, what was it? The offense goes to, let me just quickly check, how do you kick out the losing team? The offense becomes a defense, and the defense gets kicked out. So then the offense becomes a defense. But of course, before it, so that A, you do this first. So you put it into the back of the queue. Then you put part B, you do this, and part C, you take the front like this. Okay, and then of course, you keep track of what is the winning streak so far, right? Because you can remember who was the one that won at last. And if the number, the length of the streak is the right number, you print out the 2 names. And that's basically it. Everything is so small. There are only 10 people that if you really don't want to use a queue, you can even use an array and then keep track of things yourself. But, really there's no reason not to use a queue. There's not much more for me to say. So I would say just at the beginning, check how long the winning streaks are, the maximum winning streaks, and then simulate. Okay. All right. So that takes care of that first problem. The second problem, key to cryptography. So let's see here. Suppose you need to encrypt a top secret message like send more monkeys. You could use a simple substitution cipher where each letter in the alphabet is replaced by a different letter, blah, blah, blah. A better encryption scheme would vary the substitution used for each letter. One such system is the auto key cipher. To encrypt a message, you first select some secret word called, let's say, ACM, and put it in front of the message. Okay, so this is the message, and then the key, you start with this. Then the longest string is truncated to the length of the message, called a key. So basically, you take this string and then you add it to the end of your secret key. So you're using the message as part of the key. And then, of course, you don't use the whole message because the first part of it has 3 letters, so you can't use the last 3 letters. Anyway, and then A indicates a shift of 0, B indicates a shift of 1, and so on. So that's the ciphertext. Note that the letter E in the message is encrypted as G in the first time, and then C in the second time, and so on. No, sorry, in Q and S in the next 2 times. The task is simple. Given the ciphertext and the secret word, determine the original message. Okay, so there are 2 lines. Both lines contain only uppercase letters, and both the ciphertext and secret words are at most 500 letters long. Display the original. Okay, so this one, again, it's also not too bad. So you're given a ciphertext. So I don't know what the ciphertext is. X, Y, A, C, D, C, F, G, let's say. And then you're also given the key. So let's say ACM. Now, one of the things that they told you is that A is a shift of 0, B is a shift of 1, C is a shift of 2, and so on. So basically, what you're talking about in the encryption side is that you take the plain text, whatever the letter is, plus the key, the letter and the key, mod 26, assuming that we use this scheme. Right? So the first thing that you probably want to do is to convert the letter into a number between 0 and 25. And the way you do it, if you have a character like this and you read it in, then the number, the code, if you want to call it, it's CH minus the letter A. So this basically takes the ASCII code of the character you read in and subtract it from the ASCII code of the capital A. And if you happen to be A, you get 0. If you happen to be B, you get 1, and so on. So this is something that you definitely should know, how to convert a letter into a number between 0 and 25. Okay, so encrypt is this way. So decrypt means that the ciphertext minus the key mod 26. Now, when you do subtraction, it's always a bit tricky because subtraction can lead to negative numbers. So the trick is to actually always add 26 to the, when you subtract, always add the modulus at least once, and that will make sure that you don't get any strange surprises. So anyway, now that you know this is the idea, then we just basically take this one, and minus this one, and you get some number, some value, so x. Y minus C is, so you shift it back twice, so x, W, and then here, I don't know, you have to shift it back many times, so you get something, whatever it is. And now, the problem is, what do you do here? Well, what you do here this is supposed to be the first letter of the plain text, which you know. So you're going to refer to this, the key, from this point on, it's whatever you decoded. So basically what you can do, if you want, is that once you know the length of the key, so L, if capital K is the length of the key, when you decoded this 0, 1, so this is the indices, let's say, once you decoded something, you would then put this something into key bracket K plus I. Okay, whatever the I is, you would put it into the key element plus the length of the key. And then you just keep going. Of course, when you get to this stage, when you get to, let's say, this stage, if you try to write into the key, it might go out of bounds, so you have to be a bit careful with that. Or maybe you don't care, maybe you just append to the key. So if your key is just a string, which is ACM, then maybe you don't even bother with this index calculation. Every single time you decode a plain text letter, you just say key plus equals the plain letter that you just decoded. Right? Then you don't even care if you go out of bounds. You might get too many characters that you don't need, but you'll never use it anyway. So it's not a big deal. This is pretty slow if you do it a lot, but at the same time, this is only a few hundred characters, so maybe 1,000, whatever it says. Does 500 characters, it doesn't really matter. You can just do it the slow way, it doesn't matter at all. Okay, so that's the key to cryptography. I want to skip loss in translation for now, and let's look at this Brad Rover. Okay, so you have so at this point, I'm going to assume that you have at least read the problems. I'm not going to repeat much, but basically the idea is that you have some kind of a command here. It consists of 4 different letters: north, south, east, west, and you have the chance to compress this by taking some substring that might be repeated multiple times. So for example here, EEN, it's repeated once, 2, and 3 times. You can replace that by a special character called M. So every time you see this pattern, you write M, and then afterward, the second line, you write what this M stands for. So you're allowed to have one single substitution of a substring by a single letter, by one single letter M. And you're asked what is the shortest number of letters that you need, right? So here, why is it 10? Because you need this one, and then you need to say what M stands for. So altogether it's 10 characters. Okay, the new line apparently doesn't matter, so it's only 10 characters. And the string that they give you to start with is the most 100. So because it's so small, it's actually not too bad. So what you have to do, so you have a string. What you want to do is you want to say, if you want to replace a certain substring from, I don't know, I to J, let's go start to N, where you can say start includes the starting point and N doesn't, the standard C++ convention or whatever you want, doesn't really matter. If you want to know if this string is a good string, then what you do is you look for the number of times this appears in the string. So how would you do that? So let's call it string, and let's call this substring like a needle. Or let's call this pattern. So how would you know how many times this string pattern appears in this string? Well, first of all, if you do a string.find pattern like this, then it's going to return one of two things. It's going to return an index where this occurs, or string : not a position, which means it's not found. So if you get this, then of course the number of times it appears is 0. If you find this, then the number of times it appears is at least 1. So it will give you the first one. But how do you know how many there are if you find one? Well, now the next thing that you do is you want to restart your search, but not at the beginning, but at this point, right? Wherever you find it, you want to add it with the length of the pattern. And that's this point. And in string.find, there's a second parameter that by default is 0, which is the location of where you want to start. So if location is, index plus pattern.length, then you can put a second parameter here, and this will start searching only from here. And again, you ask, is there an index that you can find this substring or not? And basically, you just write a loop, right? So you can basically do something like this. Location is equal to 0. Wow. So let's see. Let's think about this here. There's an index, so you have to make sure that you get the right type. So the right type for string : size type, I believe. And then this is, let's say, int. So wow, index equals string.find a pattern starting at location. It's not equals to string : end pos. Then you just increment location, sorry, not increment. Location equals to index plus path.length. And then, of course, you probably want to have a count that counts how many times you've seen this. Right? So this loop, if you write this in a function and return the count, it will tell you that for a certain pattern, how many times this appears in the string. Okay. So now, what's the point? The point is, if you know what is the pattern that you want for the macro, then your string is basically what? Your command length, your string length, once you compress. So the length, the new length, okay, so there's a new length. It's equals to what? It's the original length. Okay. Minus the number of times the string appears times the length of the pattern, plus this many back, because every one of those patterns has to be replaced by the single letter M, and then plus the pattern.length, because you have to say it again in the second line. And that would be a new length, provided, of course, you can simplify this. There are lots of ways you can simplify this, but it doesn't really matter. I want to write it like this, so it's easy to see where I got everything from. And you get the answer. You minimize overall possible patterns. The only question is, which pattern should you use? And the answer is, I don't know. And because there are only a few hundred, maybe only 100 characters, you can just try all possible substring as patterns. And that's all you have to do. So try all possible substring. So you use the standard loop, int s equal to 0, s less than string.length, s plus plus, and then e it's equals to s plus 1, because we don't worry about empty string. S is less than or equal to string.length. Why do I use less than or equal to? Because, sorry, e. Why do I use less than or equal to? Because I am saying that e is not included in the range, is one beyond the range. And then you can say pattern it's equals to pattern is equals to string dot substring starting location at this length, and then you can run the rest of the code to figure out what is how many times that pattern appears, what is the new length, and then minimize that. Okay, so that's the breadth over. All right, now we step into a couple problems that are a little bit harder. And which one do I want to do first? Let's look at loss in translation. I'm recording, right? Let me just make sure I'm recording. Yes. All right. So there's a problem, but I'm not going to read through it too much. Basically, you have number of languages, n, which is up to 100, and then you have translators that can up to 4,500 that can translate between one language to another in both directions, I believe. Wait, maybe not. Let me just make sure. Because I'm actually saying, oh yeah, it says it can translate them in either direction. The M lines of the form L1, L2, C, where somebody can translate between L1 and L2, and then it costs you C to translate between them. The initial book is always written in English. Okay, so you want to be able to translate from English to every other language. You want to minimize the cost, but there's also something else. While minimizing the total cost of each translation is important to you, the most important condition is to minimize each target's language distance from English. Okay. So you want to, if you can translate from a language, from English to some other language in one step, you do not want to go multiple steps even if it's cheaper. Okay? You always want to take the shortest distance in terms of number of translations you do. And then if there's a tie, minimize the cost. So that's basically what you want to do. And then there's also the case that it's also it's maybe that it's not possible to translate your book to all target languages. Maybe there's for some languages there's no way to translate to that part. All right, so let's look at this a little bit. So maybe the two things that you want to do, you're going to minimize. Well, first of all, you want to translate English to everything. Hang on, did I accidentally? Okay, it's okay. So translating, minimize distance to each language, minimize total cost. Okay, so this is absolutely must. And then this is first of all, and then if there's a tie, you break this. Now, maybe we think about what happens if this is not the problem. What happens if there's no A? So suppose there's no A. You only want to minimize total cost. You want to be able to translate English to everything. Well, this means that you want to make sure that you choose a subset of edges to make the whole graph connected, and that would be a spanning tree. And this would be, of course, the minimum. minimum spanning tree. So if you didn't have to worry about distance to each language to minimize that, you just compute a minimum spanning tree of this graph and you're done. But that's not what we asked to do, so we have to think a little bit more. But it's always good to think about, simplifications of the problem sometimes and see if that helps you. Okay, so we have to do this. Now, minimizing distance of each language in terms of number translation, if we don't have to worry about total cost, then basically this is the breadth first search. You start from English, and then you look at all the things that you can translate in one step. Language 1, language 2, language 3, language 4. You look at all the things that you can translate in 2 steps. And maybe there's one here, so you ignore that. And then maybe this one and do language 6 and also language 5, and so on. Now, if the only place where you have any kind of problem is to look at here, L5, where you have 2 different ways of reaching this place in 2 steps. And then the question, of course, then is, are you going this way, or are you going this way? And you will have to minimize the cost. So how are we going to do this? Okay, so what you have to do in your breadth first search, it's basically you do a standard breadth first search where, let me get the next page. Whoop. Seems like my whiteboard application has crashed, so let me try it again. Okay, let me make sure. I think I'm okay. So what you're going to do is that you'll do the standard breadth first search situation where you have a queue of, in this case, languages. You can use strings if you want. And at the beginning, you would insert English. And now with breadth first search, you probably also have to have a distance or visited. So we probably would have like a map string int distance. Okay, so then you would also say distance of English is 0. Okay, but we're also going to have another that also keep track of how much it costs to get you here. Okay, so now what are we going to do? We do the standard loop while, not q.empty. You pick the first language, so string cur equals to q.front, q.pop. Right, so that now you're going to look at all the different things. So you're going to say for each, so I know this is not C++, target. So from each target that you can convert, you can translate from current, you ask what? Yeah, first of all, is distance of target set. Right? If you have not set, perhaps I should say. So not set means that you have never seen it before. If you've never seen it before, you just push it, right? So then distance target, it's equals the distance of curve plus 1, and the cost of target, it's equals to what? Now you have to be a little bit careful, and you have to say, well, what is the cost of this target? We are just going to use the cost of the edge, not the whole cost from beginning, from English to all the way in, because you have already kept track of these costs before. So if you have English, you have some cost, let's say 10 to get to, I don't know, Spanish, and then you have another 5 to get to, I don't know, Japanese. When you're looking at total cost, you don't want to count 15 because you already paid the 10 to get to the second. So you only want to count the 5. Okay. So that's why this cost is only the cost of the edge, not the cost of the whole path from the root. All right. So if you've never seen it before, then what else do you do? Well, you also push it into the queue. And that would be this pretty standard breadth first search. But there's one thing. The one thing is, what if there's another way in? Let's say 14 to what other language? Chinese. And then this is 3. Now, it's important to know that even though this path here has a path cost of 13 and this path has a, oops, and this path has a path cost of 17, that's not important. What's important is this number here. Okay, this cost is actually better, even though your whole path is more, because you only add 3 more. So we need to be able to detect this. So how would we detect this? So else, no, let me change that to blue. So else, if the distance of target is exactly the same as the distance of curve plus 1. Okay, so why do I have to do this? Because I want to make sure that the only time I consider this tie breaking is if the distance that it says another way in with the same distance. Otherwise, I do not want to override the cost. Okay, so else if this distance, the distance of the target is exactly the same as distance of curve plus 1, so it's a tie break. And what? And the cost of the target, it's bigger than the cost of the edge. If that's true, then you want to do this all over again. Or in other words, you can actually combine both of these into a more compound if then else, if this or this. And then at the end, all you have to do is just add up the cost for every single language that you've seen, and that's your answer. All right, so this is a modified breadth first search. And you have to be a little bit careful about the tie breaking. And I guess that's all I have to say about this. Okay. The last one, hang on, I'm going to actually stop this recording. I think I'm not absolutely sure that I was sharing this. Let me stop the recording. Let me play it back and make sure that it actually works.